the mathematicians have come up with some names that probably are not that difficult to understand, but probably you didn't hear those names before, so I'm going to just explain to you those names, and from now on we can use them in the course. Most of the common thing that will be used in this course is Galois field, GF. To get to Galois field, we have to start from the group. So a group is any element, any set that is closed with respect to some operation. And closed means that the result of the operation is also in this set. So for example, and the operation we can call dot, we don't know what dot is, but if we do A dot B dot C, if it is associative, that means operation can be done in any order. It has an identity, so there is a E which when the operation is done, it remains the same thing, has an inverse, and so on and so forth. And if, so this is any such thing is a group. And we already saw a group before a minute ago. Right? But there are other groups which don't have to be numbers, this could be just ABCDs. The operations don't have to be addition, multiplication, there could be some operation. Alright? If the operation is commutative, which is not necessary, if it is commutative, then it is called an abelian group. Abelian group. So for example, subtraction is not commutative. So you will not use any set with subtraction, and I mean it won't be an abelian group with respect to subtraction. Right? But it could be abelian with respect to addition, multiplication, and all that. Now Z8, the group that we saw a minute ago, is a group with respect to modular addition, and the identity is 0. We noticed that it was not a group with respect to multiplication because there was no identity. Oh, because inverses, the third property was violated. There were no inverses. You can apply the operator many times. So if you apply the operator 3 times, we could call it cube. And if every element is a power of some fixed element, then we call it a cyclic group. Now this is important, is that suppose you have a set which has 8 numbers or 8 elements, and every element is power of some number. Then that is cyclic group. So not every group is a cyclic group. So let me give you an example of a cyclic group. I just added 0 there. I think 0 has to be there. But basically, if you have taken 1, 2, 4, 8, all of these can be generated from 2. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8. And this is a group for multiplication, mod 12 multiplication. So when you multiply, the result comes out in the same group. But all the members can be generated from one element 2. 0 somehow, and I've seen, this is where I was not for sure, but I've seen in all the examples worked out everywhere, 0 is somehow given as exception, where exception basically 0 is a power of 2 actually. I mean, if you really think about it, it's minus infinity. But and you multiply 0 with everything else, the result is in 0 here, so that it satisfies all of that property except for what is the power of 2, and so there is a power of 2 which is 0, right? So the whole group satisfies the property that we talked about. Alright, so this is a cyclic group. Look, this is a mod 12, this is a cyclic group with mod 12 multiplication. So when we talk about mod 12 multiplication, in this group only, right? So we're not talking about number 11 here because that is not a member of the set. So some groups are ring. Which groups are ring? The rings have 2 operations, which can be called addition and multiplication. The group has to be abelian with respect to addition, and the multiplication have to be associative, and the multiplication has to be distributive. So we have seen all of this. So everything that we saw before, like mod, not in mod 8, but we saw it in the mod 2 arithmetic, for example, that was all a ring. Those were the rings, right? And then if the multiplication is commutative, then that is a commutative ring. And if the multiplication has an identity and no 0 divisors, then it is an integral domain. Alright? So basically, more and more restrictions you put, you get a smaller set of such groups, and they get a name. All right, so here's the homework. So here's a set. It has 3 elements, A, B, C, and the plus operation is defined as in the table. And the multiplication operation is defined as in the table. Now you have to verify that all those conditions are satisfied for the ring or not. Is S a ring? So you have to see whether obviously you see that this summation, it is closed with respect to summation because the result of the summation is in the set, and it is closed with multiplication because the result of the multiplication is in the set. The question is whether all of these other things are true. A plus B is equal to B plus A. Is it commutative? Whether this is associative, whether it is distributed, and all that. Right? So you write down 5 conditions and write down whether this is true or not. If one comes out false, the answer is no. If all of them are true, the answer is yes. But you have to write down all the conditions and show that those are true. So far what we have done is, we are going to get to the last thing, is called a field. A field is an integral domain in which each element has a multiplicative inverse. So the important thing about the field is now we need an inverse. So we saw an example of a set which was not a field. Anybody remembers what was that set? Z8 didn't have a ring, didn't have the inverse of 2. So if the inverse exists, then we call it a field. So here are the set of properties. If it is closed, associative, additive identity, and additive inverse, we call it a group. If it is commutative, we call it abelian group. If it is closed under multiplication and associativity of multiplication distributive law, then this is a ring. If it is commutative multiplication, it is a commutative ring. If multiplicative identity exists and no zero divisors, then it is integral domain. If it is a multiplicative inverse, then it is a field. All right, keep this picture in front of you. Whenever you have to test out whether it is a ring or a group or a field or what, So this is all the sets, properties that we need. 1, 2, 3, 4, 5, and 7. 12 properties. So the final thing, we reach the final thing that we want to reach is the Galois field. Galois field actually are also called finite fields. Finite field means finite. It means they're not infinite. I mean the number of elements is not infinite. Finite fields. And a field with a finite number of elements is called finite field, and it is also called Galois field, and generally written as GF with the number of elements inside it, which generally has to be a power. If it is a field, it will always be a power of a prime, p raised to n. P is a prime, n is some number. If it is not a prime raised to n, p raised to n, it is not a Galois field because it will not satisfy one of those properties. So the number of elements is always a power of a prime number. So if n equal to 1, then G of p is a set of integers with arithmetic operation modulo prime p, can do addition, subtraction, multiplication, and division without leaving the field G of p. If it is a field, then you can do all of these operations. G of 2 is basically has 2 members, 0 and 1. And you can do everything, multiplication, addition, subtraction, and the result will come out 0 or 1. G of 8 would be mod 8 arithmetic, but you have to define that carefully, as we will show you in a few examples later on, not just the way we did it, okay? There is no G of 6 because 6 is not the power of a prime. So here G of 7, G of 7 is actually straight mod 7. So in G of 7, if you take, these are the 6 elements, the product is defined as a standard method. Everything times 0 is 0, everything times 1 is the same number, everything times 2 is whatever number, like that. You can define straightforward way, and you could have done the addition and everything else. So G of 7 is a Galois field. Now the things become a little bit more complicated. So far we were talking about numbers. Now we will talk about polynomials. So any polynomial can be written as a power of x. So this is a polynomial of order n, of order n, because the highest coefficient which is non-zero is x raised to n. And now you know, all of you should know, and I'm not going to teach you here, how to add, subtract, and multiply polynomials as usual, right? That is something taught in the algebra, again in high school. So I assume that you know that part. And you can find the remainders and the quotient. Not a straightforward mod 8 arithmetic, but we have an example coming up where we can do it with the polynomials. So it will come up back in polynomials. So some polynomials have no factors and therefore they are prime polynomials. You know how to factorize a polynomial, and if you cannot find a factor, then that's a prime polynomial. So polynomials have the same properties that the numbers have. So that is the normal arithmetic that is taught in high school. What is not taught in high school is probably the polynomial arithmetic with mod p coefficient. Mod p coefficient means they probably don't teach you how to do mod 8 or mod 7 or mod 3 or 2, polynomials. And that we will teach you here. The next step would be to teach you mod p coefficient but mod mx operation. So the coefficient will be mod, say for example 8, coefficient could be mod 8, so coefficient would be between from 0 to 7, but really the whole polynomial thing we do with mod mx, with some other polynomial. So let's do mod 2 coefficients. So here is an example of a polynomial which has mod 2 coefficient, only 0 or 1. So we can call it x cubed plus x squared, and the coefficient of x is 0, coefficient of 1 is 0. Right? The coefficient of only 2 terms is 1. And gx is another polynomial. In this case it is a polynomial of degree 2, and all the coefficients are non-zero. If you were to add these two, what will you get? X cubed, you get that. Now x squared is here plus x squared is here. How much you get? 2x squared. 2x squared is same as 0x squared. 2 is same as 0. Either you think that way or you think in terms of exclusive R. So 1 exclusive R1 is 0. For at least for mod 2, the exclusive R is a good way to think, okay? Anyway, so you got 0x squared plus 1x plus 1. That's the sum. Multiplication. Now this one, to do this, you really have to do long multiplication. So we want to multiply fx by gx. So x squared, x cubed plus x squared. We want to multiply by x squared plus x plus 1. First we multiply by x squared, we get x5 plus x raised to 4. Then we multiply by x, so we get x4 plus x3. Then we multiply by 1, we get x3 plus x squared. Then we add up all of these, we get how much? x5. So you can get that fx times gx is x5 plus x squared. You want to divide, you can do the division same way. You could divide and then you could get a quotient and a remainder. Remainder would be less than the divisor basically in degrees, right? As long as the degree is higher than the divisor, you keep dividing until you get the remainder. And so Rx is the remainder. That can be said as the fx mod gx. If there is no remainder left, remainder is 0, that means there is perfect division, and gx divides fx. And fx, if gx has no divisor other than itself and 1, we say that it is prime polynomial. Just like a number, if you cannot factor the polynomial anymore, then it is called irreducible polynomial or prime polynomial. Okay? Now, let me just give you some examples of the polynomials that are reducible and that are not reducible. So x plus 1, what are the factors of this? There is no other factor. Basically, x plus 1 is equal to x plus 1. You cannot factorize it anymore. So this is a prime polynomial. Right? What if I wrote down x squared plus 1? Can you factor that? X squared plus 1 is equal to x plus 1 times x plus 1. Okay? In fact, when you do it x squared plus 2x plus 1, 2x is 0, so you get x squared plus 1. So this is not a prime polynomial. What about x squared plus x plus 1? That's a prime polynomial. You can try it out, there's no factor. And so on and so forth. Now, just like you can do Euclid's algorithm for numbers, you can do Euclid's algorithm for polynomials. You take the big polynomial, divide by the small polynomial, get the remainder, then keep dividing until you get a 0 or a 1. Until you get a 0, yeah. If you get a 0, that means it is a perfect division and you got the common GCD, greatest common divisor. If it comes out 1, then you know there's the inverse, and so you can find the inverse of polynomial. So here is an example of mod mx arithmetic. So everything here is done with respect to this polynomial. So when I ask you to add, let's say, two numbers, first number is, okay, by the way, every polynomial has a corresponding numeric representation whenever the Galois field is 2 raised to n. So for example, x is represented as 0, 1, 0. Why? Because the second power is 0, first power is 1, and the 0th power is 0. Coefficient is 0. So these are all the coefficients. If I gave you a number 1, 1, 1, that means x squared plus x plus 1. If I gave you 1, 1, 0, that is x squared plus x, and so on and so forth. So these numbers are same as these polynomials. Similarly, these numbers are same as the same polynomials here. Now, if we were to add these two polynomials or these two numbers, we will get something here. So let's try this one. I'm going to add x plus 1 and x plus 1. Okay? What do we get? 2x plus 2, which is 0. Right? If I add x plus 1 and x squared plus 1, I get x squared plus x. 1 cancels out. I can write this as a number. X squared plus x is what? X squared plus x is 1, 1, 0. So I could have written that 1, 0, 1 plus 0, 1, 1 is 1, 1, 0. So you can write it in binary numbers or you can write it in polynomials. Same thing. Now, addition is easy. Now multiplication. Multiplication may require you to do this long multiplication. But if you do that, then you get x plus 1 times x plus 1. You get x squared plus 1. Just like we did there. If you do x squared, multiply it to x squared plus 1, you get x. Why x? So let's see why you get x. If you multiply x squared to x squared plus 1, you are multiplying x squared to x squared plus 1. You get x raised to 4 plus x squared. Right? But x raised to 4 is more than our modular, this one. So that is modulus. Our modulus is x raised to 3. Right? So we have to reduce it to that, below that. So we just subtract x raised to 3 plus x plus 1, right? Plus x plus 1 times x. You have to subtract this quantity from this to bring it down below x raised to 3, right? So this is x raised to 4 plus x squared plus x. You subtract that and you get x. Here. This cancels out, this cancels out. So that's the multiplication of those two. So we got an x there. Yeah, let's do another example of multiplication. Choose one. X squared. Can you say it in English?
X squared plus x plus 1.
X squared plus x plus 1 times
The same polynomial.
same polynomial. Okay. So we multiply this by longhand. Multiply by x squared, we get x raised to 4 plus x raised to 3 plus x squared. With x, we get x raised to 3 plus x squared plus x. With 1, we get x squared plus x plus 1. We add up, we get x raised to 4 plus x squared plus 1. Good so far? Okay, now this is more than 3. Right? So we start subtracting. First thing we subtract is x raised to 4. Basically what you could do is you could just divide it by x raised to 3 plus x plus 1. When you divide it by long division now, you must divide by that, you take x and you get x4 plus x squared plus x. Cancels out, you get x plus 1 here. Right? Now this is less than that, so this is remainder. So the answer is x plus 1. X squared plus 1 times x squared plus 1 is x plus 1. You first multiply longhand and then you divide longhand to get the remainder. There's a lot of longhand division here in this chapter actually. Alright, so here are some more examples. I think we probably did all of these anyway. Coefficients are 0 and 1. So if you want to multiply, if I could give you either the polynomial or the number. I could say, okay, multiply 1, 0, 1 and 1, 1, 1. If I give you numbers, you have choice of doing either way. You could do it by, at least in the 2 raised to n GF, actually you can do either way. You could just do by numbers or you could do it by polynomials. So let's just do this thing by numbers. Let's just, whatever we did a minute ago, let's just do it by numbers. So this, what is the number representation for this? That number is 1, 1, 1. Right? And we are multiplying by this number, and that number is times 1, 1, 1, 1. Right? We could multiply it. First we take this one and we write down 1, 1, 1. Then we multiply by this second one. So we take 1, 1, 1. We multiply the third one. We do 1, 1, 1. We add up. We get 1, 0, 1, 0, 1. Exactly that polynomial. Right? Now since this is more than our number 1, 1, 1, so we divide it by 1, 1, 1. First we go by 1 like that, and then we get 0, 1, 0, 0. Alright, and this is still more, so we divide by 1 more time, so we get 1, 1, 1, subtract, we get 1, 1, 1, check 1 more time, or we did make some mistake somewhere. So 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, what did we do here now? X cubed plus x plus 1. Oh, that was a different arithmetic. So, x cubed plus x plus 1. I wrote down, okay, okay. So, that one we really have to do it by polynomial. So, because that's actually what we are doing here is we are doing multiplication of these two mod what I would call x cubed plus x plus 1. X cubed plus x plus 1 is 1, 0, 1, 1. Right? So we have to do mod like that. So we have to do here 1, 0, 1, 1. And the whole division would be 1, 0, 1, 1. And you get 0, 0, 0, 1, 1. So you can just work on the coefficients. Basically that is just like working on the coefficient, not writing the x's. Alright, so you have to know what are the coefficients, and then you have to know what is the modulus, with respect to which we are defining these things. So that polynomial has to be kept into mind. Alright, so addition, multiplication, and then reduction. Okay, thank you very much. This is Michael, and you can basically reach him for any problems. Some people have problem with the logging in remote desktop, and so I don't know whether the permissions need to be set for them or whatever. All right, so this is all clear, right? how to do multiplication, division, and all that. All right, so this is your homework. Determine the GCD of the following pairs of polynomials. So you have to find out the greatest common divisor of these two in GF11. All right. So basically, the numbers cannot be more than 11. So that means 11 is 0, and the rest of the rules we talked about. All right. And actually, I will show you the answer in a minute at the end of the slide, so that you know exactly what the answers would look like. But anyway, so the last slide actually is that sometimes we want to generate everything by one element. So you could have a polynomial that generates all the members, all the polynomials of that set. So you could have polynomial z that generates all the polynomials, just like we saw in the number case. That would be a cyclic field or something like that. Cyclic group or cyclic field, when the elements can be generated just by power. That brings you to the end of this mathematical chapter. This is only half of the mathematics, because the other half comes later, not basically in this lecture, but after one more chapter. Chapter 7 I think is another mathematics, but chapter 4 is done, and what we have learned is these 7 things. First of all, I think you learned is the tabular method for Euclid's algorithm, right? And if you do that, the advantage of that method is that you get the inverse figured out easily. Then we learned that there are groups and rings and fields and Galois fields, and the main thing is that these could be defined on the polynomial or could be defined on the numbers. Right? Everything that we talked about, addition, multiplication, division, subtraction, can be done in the polynomials or in the numbers. So we started first with the numbers, and then we introduced the polynomials. So if you do numbers, or either one, the group is an element and operation. You need an element and an operation that should satisfy the 4 properties. Abelian group would satisfy commutation. The rings will satisfy addition and multiplication. Fields will have commutation and the multiplication identity and inverse. Finite field will have finite number, and therefore they will have only 2 kinds, either p raised to n. Well, they have only one kind, p raised to n, which generally p is either equal to 2 or n equal to 1. See, that's another thing. I didn't mention that, but I haven't seen p squared or p cube or anything else. 2 cube, 2 raised to 5. So if p is 2, then we do all these powers. Otherwise, generally it is just prime number, power 1. And then in 2 raised to n, this should be 2 raised to n. G of 2 raised to n also form a field.